What's the name of the disorder where the walls of the blood vessels become weakened?
Low blood pressure.
Yeah, aneurysms, right? Aneurysms. So an aneurysm is a situation where the walls of the vessels become weakened. Is that a bigger problem on the venous side or the arterial side? Arterial side, right? And remember, the arterial side is high pressure. So you have high pressures, thinned walls. Those walls now are at greater jeopardy of rupturing. And because it's a high pressure side, Ohm's law tells you that if pressure's high, then what must be high? Oh, come on. Flow rate will be very high. So imagine you have an aortic aneurysm and the aorta ruptures. What do you think? Are you going to save that person? That person's going to bleed out in about 2 or 3 seconds. So they're going to be standing there looking at you. They're boom. They're going to be down on the ground. Absolutely nothing you can do. You would be lucky if you had them on the operating table and happen to have their chest cracked open. You might have a shot at saving them. But these are absolutely fatal types of injuries where you have a blowout, so to speak, of a blood vessel on the high pressure side. Okay, so this is kind of our basic anatomical consideration with respect to the valves, the chambers, key blood vessels. So now we're going to kind of talk about the anatomy of the heart from a slightly different perspective. And we're going to refer to this as the conduction system of the heart. A couple things I forgot to mention in that last diagram, and I'll talk about them here. If you sit there and try to imagine the longitudinal axis of the heart, the longitudinal axis of the heart, to think about that, what are we going to call the tip of the heart right here? The apex of the heart, very good. What are we going to call this muscular wall that separates the left and the right ventricles from one another?
Septum.
Excellent. Septum, yep. So we've got the septum. So now let's talk about the conduction system of the heart. And as it turns out, the heart has a very unique set of cells, and these are called pacemaker cells. So now we're back to electrophysiology. So Mr. Niddle, to answer your question, do you need to know things that we've talked about previous in this class? The answer is?
Yes.
Yes. So having said that, Mr. Niddle, glad to hear you believe that. So we're going to talk about electrophysiology and membrane potentials. What am I going to put on the y-axis?
The membrane potential in millivolts.
Good, excellent. So we've got membrane potential, and the units are millivolts. So now, being the great students you are, I know all of you are going to go home tonight and you're going to review your lectures on neurophysiology. You would tell me, first of all, let me put the axes in here. So we have minus 100, minus 50, 0, and 50 millivolts. And then we're going to put time down on the x-axis. And this is going to be in units of milliseconds. And Ransom, you're going to tell me that the resting membrane potential will be right around what? You're good. You're an excellent ventriloquist. Say that again. Let's do that again. You're going to tell me that the resting membrane potential is? No. Come on. You're supposed to project your voice out over here somewhere. Minus 70 millivolts. We're going to say that there's this magical membrane potential called threshold. And so here's your cell at minus 70 millivolts. In a normal excitable cell, if there's no stimulus, then the membrane potential does what, Ms. Sharon? There's no stimulus, what happens to the resting membrane potential? It stays constant, that's right, at, say, negative 70 millivolts. So that's the majority of excitable cells. They have stable resting membrane potentials. In other words, if they're not stimulated, if they're not excited, they just stay at minus 70 millivolts. The heart has got a very unique cluster of cells in the right atrium. And I'm just going to represent the presence of those by this little asterisk, the star symbol. And these cells are collectively known as the sinoatrial node. I'm going to put S-A node. And in parentheses, what I want you to write is that this is the pacemaker of the heart. Now, in electrophysiology land, when you use the term pacemaker, that means something. It's not just, oh, okay, we're going to give it that cute little name, pacemaker. Pacemaker cells have very unique properties, and here's what happens to them. In pacemaker cells, they have resting membrane potential that spontaneously rises towards threshold. And when it hits threshold, then these pacemaker cells will generate an electrical event known as an action potential. And then they'll repolarize, return back to the resting membrane potential, and then slowly but surely they will rise. The resting membrane potential will rise towards threshold, and you guys would tell me that once again they would generate an action potential. So in green, what we're talking about is an excitable cell with a stable resting membrane potential. What makes pacemaker cells so unique is that their resting membrane potential is not stable, it's unstable. And Miss Elgin, the rate at which these pacemaker cells fire is dependent upon what? The rate at which these pacemaker cells fire is dependent upon what?
On how fast it's stimulated, how often. I guess tetanus or something.
No.
Is it beats per minute?
Demand or blood demand?
No.
Is it beats per minute?
No. So the question I'm asking is a simple
Timing
one.
here.
The rate at which these cells depolarize is dependent upon what?
Opening of
Dependent upon the slope here, right? If the slope is really steep, then they move towards threshold very rapidly, and therefore the firing rate will be relatively high. On the other hand, if the slope is slow, then they move towards threshold at a slow rate, and you would tell me that they fire at a slow rate. So, your sympathetic and your parasympathetic nervous systems, as you guys are going to learn here very quickly, release neurotransmitters. Oh my goodness, I forgot the names of these neurotransmitters already. Mr. Cherness. Parasympathetic neuron. What type of chemical messenger will they be releasing on these cells right here? Can't remember? Okay, I like your honesty. What's that? That's correct. That's exactly right. And sympathetic neurons that act here are going to release what type of a neurotransmitter? Norepinephrine, that's right. And so if you come along, parasympathetic slows down, sympathetic speeds up. So if I stimulate the parasympathetic nervous system, as you guys will tonight when you go to bed and you're lying there, all of a sudden the parasympathetic nervous system and its activity goes up. It releases more acetylcholine here, and your heart rate will go down. How does that happen? Because it changes the rate